The long and winding vector route that leads us from A to B doesn't change its final value, no matter what path we see. Always the same. This vectors set us free. Do you know that song? It's an old one, but it's still massively famous. That's the Beatles, and very appropriate for the topic that we're doing today, which is algebraic vectors. So last week we were doing column vectors, and just to recap, we talked about what a position vector is. So if we have a point here, A, 4, 7, then we could say that the position vector of that point, in other words, the vector from the origin to that point, is, well, 4 along the x and 7 along the y, but we write it as a column vector like that. So that's the position vector, and here I've just named it. I've called it the underlining on the small letter a tells you that that a is not a number but a vector. And then we talked about relative vectors, and we said, look, if we want to find the vector from A to B, we talked about the relative vector rule. The relative vector rule says the vector from A to B is equal to the position vector of the position vector of B minus the position vector of A. So in this case, the vector from A to B would be the position vector of B is 6, 1, minus the position vector of A is 4, 7, and so that's going to give us 2 minus 6, and that gives us the relative vector from A to B. So that's what we were doing last week. Now, if we're not going to put those numbers on anymore, then we could call it algebraic vectors. So we're describing positions and directions relative to these reference vectors. So A and B now become our reference vectors. A and B become our reference vectors. And we're still doing the same thing. We're saying the relative vector from A to B is the position vector of B minus the position vector of A. So it's B minus A. But the difference is we're not actually writing those coordinates anymore. So we're not looking at the absolute coordinates on a grid. In fact, we could just get rid of the grid completely. So that's what we mean when we talk about algebraic vectors. We're not actually specifying what the coordinates of A are anymore, and we're not specifying what the coordinates of B are anymore. Why might we do that? Well, rather than using our x and y axes, using some A and B as reference vectors, it might be useful because we might be in a situation where there are some intrinsic vectors there already which are not aligned with the x-axis and not aligned with the y-axis. So for instance, this is my attempt at doing a diagram of a crystal lattice for a hexagonal close packed crystal structure. And in this structure, the natural direction for A within the crystal itself would be A is root 3 and minus 1. And the natural vector for B would be B is root 3 and plus 1. And so rather than using the x and y axes as our axes, if we use these as our reference vectors, as our basis vectors, then things will just naturally work out simpler. So I can show you what I mean with reference to a little thing that I created in GeoGebra. So you can see I've got these points A, B, C and D, and you can see that you could probably guess the coordinates of B are 1, 2, 3, 4, 5, 6, 7 along the x-axis, 1, 2, 3, 4, 5, 6, 7 along the y-axis. So 7, 7. You see the coordinates of A, C and D, and you could work out all those coordinates. But what I'm telling you is that actually this shape is it has an intrinsic structure which uses these two vectors. So one of the vectors is 2, 1 and the other vector is 1, 4. And if I change my grid so it uses this as my basis vectors, you'll see what happens. And so all of a sudden, you see the shape becomes much simpler. Using these as my basis vectors, if I start with, say, let's start with B here. Let's start with B here. And then let's say, I know I'm going to need some vectors parallel to A. So I'm just going to change the lambda. So it tells me that this vector here is 2A. Okay. And now I'm going to move I'm going to move this point here to, say, A here. And I'm going to say, what is the vector from A to D? And I'm going to again increase lambda. And then I'm going to increase mu. No, I'm going to decrease mu. Okay, so that tells me that this vector is 4A minus B. So I can write that as 4A minus B. And then now I can move my point here, A, and I can move it to, say, here. And this time I'm going to get the lambda to 0, and I'm going to increase the mu. And then that tells me that that vector is 2B. So this vector here is 2B. Okay, and so we can write these with reference to these vectors here, A and B. And again, if I just show you the original grid, that's what that looked like on the original grid. And you can see it wasn't so obvious. These coordinates were not so obvious on the original grid. There was no obvious link between these two. And the links become a lot clearer using my changed grid. Okay, so here I've got a similar situation again. I've got some points here, and this time I've realized that these two might be relevant vectors for this grid. And so if I change the grid to look at it using those two vectors, then you can see that the points seem to be a lot clearer. And so I'm already at B here. Let's work out the vector from B to A. So I'm going to go 1 along lambda, and I'm going to go 1 along mu. So I can tell you that this vector here is A plus B. And then now I'm going to just change these. I'm going to make mu like that. And so that tells me I'm at 3A minus B. So this vector here is 3A minus B. So 3A minus B. And if I go back to the original thing, so, you know, in this case, A stands for 3 minus 1 and B stands for 3, 4. So if I insert those vectors in place of A and B, then you'll still get you'll get back to the original coordinate geometry, the Cartesian grid for that. Okay, so here's my third example. And again, you can see I've got this shape here, and I've decided that these two vectors are going to help simplify the grid for looking at this shape. And so I've drawn in those two vectors, and then I'm going to move my point here to B, and I'm going to figure out what the vectors along each side would be. So that would be A plus 2B. So that would be A plus 2B. And then I can just change it so that that's there. So that's going to be 3A minus B. So that's going to be 3A minus B. That's going in that direction there. And this one's going in this direction here. And then I can move my point to, say, here. And then I can increase oops, too far. Whoops, too far again. Okay, and so that's 5A plus 3B. So that vector there is 5A plus 3B. Okay, so equivalent vectors, parallel vectors. This doesn't really change now that we're looking at algebraic vectors. So for instance, which vectors are equivalent and which vectors are parallel? So it looks to me like these two vectors here are the same as each other. So if I take this vector here and then plonk it onto there, you can see they match exactly. And so those two are equivalent vectors. So I can relabel this one as just being A. So I can relabel that one as being A. This one looks like a smaller version of A. It looks like a smaller version of A. Let's just okay, so I think, I haven't drawn it very well, but I think that you need 4 of them to make up A. So I think this vector here would be a quarter A. So I think this vector here would be 1/4 of A. And then similarly here, this one and B, it looks like you're going to need a few of the B's. I think we're going to need 3 of them. Yep, that seems to, oh, that went a lot better, didn't it? Okay, so that means that this vector here must be 3B. So this vector here is 3 lots of B. And now we have an unusual situation because this one's pointing in the wrong direction. So it's sort of matches with C, but it's in the wrong direction. But also you'd need 2 of them to make up C. So what I'm going to do then is to call that, well, if the arrow were pointing this way, I would call it 2C. So if the arrow were pointing this way, then I'd call it 2C. But it isn't. It's pointing the opposite way. So to account for that, I'll call it minus 2C. Minus 2C. Okay. So comparing vectors and looking for parallel vectors. So we saw from the last page that parallel vectors have the same direction and different lengths. I mean, I say they have the same direction. They could be pointing 180 degrees in the opposite direction. And we'd say that's still the same direction, but the negative version of that direction. What's this? Eyes, F-A-C, what does that mean? Oh, you know what that means. In factorized form, it's easy to identify parallel vectors. So what they're saying is, look, you can't tell that these are parallel, but if you just factorize them, so if I just factorize them, from this one I'm going to factorize a half out. So that's going to give me a half. And then that's going to give me 4A minus B. And this one I'm going to factorize 3/8 out. 3/8. And then that's going to give me, well, if I want to make that over 8, I'm going to have to multiply top and bottom by 4. So it's going to be 4A minus B. So when you factorize them, what you notice is the bit inside the brackets is identical. And that tells you that they're parallel vectors. So that immediately tells you they're parallel vectors. And then the next thing here, the half and the 3/8 tells you the change in the length. So the multiplier from here to here, you find the multiplier, you know, by doing second one over first one. So the multiplier is times 3/8 over 1/2. And you know, you can cancel that down. That's going to become a 4 and that's going to become a 1. So it gives you times 3/4. So what that tells you is that AB, the vector A to B, times 3/4 times 3/4 times 3/4 gives you the vector P to Q, gives you the vector P to Q. In language terms, that means, number one, they are definitely parallel. They are parallel. You can only ever write this sort of a vector equation when they're parallel. So that's the vector equation that you write. You write one relative vector is equal to k times another relative vector. So whenever you can write that, it tells you they're parallel. And number two, it tells you that PQ, its length, the length of PQ, is 3/4, shall I just write 3/4? Shall I write 75%? I don't know. It's 3/4 of the length of AB, So that tells you PQ is 3/4 of the length of AB. So it's not quite as long as AB. It's 75% of the length of AB. AB is the longer one. Okay. so this is your question 1. You've got 9 different vectors there. You have to find all possible pairs of parallel vectors. And for each parallel pair, you have to form a vector equation like we did on the previous page and describe the relationship like we did on the previous page. So saying it, take a screen grabber there. It will be linked underneath as well. So like we did on the previous one, you have to write a vector equation like this. So some sort of vector, I don't know why it keeps doing that. It's flicking backwards and forwards. Some sort of vector equation like that, and that vector equation leads to 2 conclusions. Number 1, they're automatically parallel. You can only write that equation if they're parallel. And number 2, this number here tells you what the length of one is in proportion to the other. Okay, so you have to do that for all of those questions. Okay, let's move on. Okay, so this was the last one we saw in the example, and we worked out these vectors. We worked out that that was 3a minus b, and that was a plus 2b, and that was 5a plus 3b. And it says compare BA and CD. We didn't actually work out CD, but it's okay because we can use vectors to work out. We can use a vector root to work out what the vector CD is. So the vector from C to D. Now obviously the quick way of going from C to D is just along there, but we don't know that road. It's not labelled for us. Our sat-nav has never heard of that road. So what we're going to do instead is we're going to go the long route. Okay. Now obviously in real life, going the long route is, you know, you're going to use more petrol and it's going to take you longer and stuff like that. But in maths life, it doesn't make any difference. It's exactly the same. Okay. So we're going to go this way. Whoops. Why did it do that? Okay, let's do that. And let's do that. Okay, so we're going to go that route. So that route, just to detail it properly, from C to D, we're going to go from C to B, and then from B to A, and then from A to D. Now, vector route should connect up, which means that whatever letter you end on here should be the letter that you start on there. So whatever letter you end on here should be the letter that you start on here. And then equally, whatever, I'm going to use the thicker one, whatever letter you end on there should be the letter that you start on there. And also, finally, this letter and this letter should be the same as those two. Okay, so that's a vector route. It's simple, it's an obvious thing. You want to go from Charlie's house to Dina's house. So you don't know the route, but you know that Barry knows Alan, who knows Dina. So you say, all right, I'm going to go to Barry's house, and then Barry's going to take me to Alan's house, and then Alan's going to take me to Dina's house. Seems a convoluted route, but if you don't know the other way and you don't have a mobile phone, so you could just ring them instead. I don't know what's going on there. Okay, anyway, let's carry on. So C to B, well, it's the negative of this because that's the vector from B to C. So the negative of that is going to be negative 3a plus b. Plus b to a is this vector here, which is a plus 2b, and plus a to d, which is 5a plus 3b, plus 5a plus 3b. And then just tallying them up, so that gives us 5a, plus another a is 6a, minus 3a gives us 3a, and it gives us b plus 2b, which is 3b, plus another 3b, plus 6b. Whenever you can factorize, always factorize your vector, because then it will tell you if things are parallel to each other or not later on in the next part of the question. So 3 brackets a plus 2b is my answer for the vector C to D. Okay, so I found the vector C to D. Okay, what's it saying now? Well, it says compare BA and C to D. Okay, so BA was this vector here. Let's just write it underneath. BA, B to A, whoops, I'm on thick pen, was this vector here, which was a plus 2b, which was a plus 2b. And the first thing you notice is that these are the same. The bit inside the brackets is identical. And that immediately tells you that they're parallel vectors. And then this doesn't have a number in front of it. We can just give it a number 1 then. That will do. I'll just put it in grey, pale grey. Just put a little 1 there. And then looking at these two, I can tell you that the multiplier from here to here is times a third. So this is, I mean, you can go the other way if you prefer. Maybe that would be nicer. I'll go this way. I'll go this way. So the end of the arrow divided by the front of the arrow, so 3 divided by 1, so times 3. And so beta A times 3 equals C to D, equals C to D. So that tells me, number 1, they are parallel. And number 2, that C to D, its length is 3 times the length of beta A. This is 3 times as long as that. And you can see that from the diagram. And to be honest, you can quite clearly see that they are parallel from the diagram. And the reason is the diagram is drawn on a proper grid, so everything is relatively correct. So if you see this arrow here, let's try and draw it. Let's try and draw it with a big thick arrow. If you see that arrow there and you clone it, you should find it's parallel to this one here, which it is. And you clone it again, and you clone it again, and you should find it's equal to 3 of them is equal to what matches the length from A to D. So that vector beta A, 3 of those vectors would give you the vector from what is that, C to D. F lies on CD. C to F colon F to D is 1 colon 2. So this is dividing a vector into a specific ratio. So we've already found the vector from C to D before. We found it in the previous question, and we said that, look, the vector from C to D was equal to 3 times A plus 2B. We already found that before. And now they're saying, no, but we want to divide this up. We want to divide this up into ratios. And the ratios that they're talking about is they're saying this, that C to F is 1 part. And then this will be 2 parts. So 1 and then another 1. Okay. So I'm going to try and write that down. I'm going to try and write that down. But I'm going to try and write it down. Can I write it down pale? No, not really. Okay, I'll just try and write it down using a pale colour. So this is 1 part. I'm on highlighter still. Let's go to pen. So this is 1 part. And then this is 2 parts. From here to here is 2 parts. And that's 1 part from there to there. Okay. So what I can do is I can just use, our GCSE knowledge from, way back first year GCSE knowledge from when we did the scale factor method. And we might say something along the lines of C to F is 1 part. And we might say C to F, that was supposed to be. And C to D, well, that's the whole 3 parts. 3 parts. And so we might say, what's the multiplier from here to here? Is times 3. So times 3. And so we might say C to F times 3 is equal to C to D. But we already know C to D. C to D was this. So C to D was 3 brackets A plus 2B is equal to 3 C to F. And then we can divide both sides by 3. And so we can say C to F is just A plus 2B. Okay, so that was pretty straightforward. And then it says find O to F. So we already know C to F. So if we want to get from O to F, we can go along this route here. We know this route now. Let's mark it on with a... let's try and use a brown pen. I don't think we've got brown here, but we'll just try and use something that's a bit brownish. Okay, so we know this is now A plus 2B. And so it says get from the origin to F. So to get from the origin to F, this is the route I'm going to take. I'm going to go from the origin to B, and then I'm going to go from B to C, and then I'm going to go from C to F. And then just to write that all down fully, I'm going to write O to F equals O to B plus B to C plus C to F equals 2B, that's that one, plus 3A minus B, that's that one, plus A plus 2B, that's that one. And then just tidying up, we've got 3A plus another A, which is 4A, and we've got 2B minus a B, which is 1B, plus another 2B, so that's plus 3B. So 4A plus 3B is O to F, and that won't factorise. If it factorises, I'd factorise it, but it won't, so I'll just leave it like that. And so there's the vector O to F. Okay, so this is your question 2. And you've got to do kind of the same thing as I did before. They've given you the vector P to Q, so you can just label that on your diagram. You can call it 8A minus 12B. And then they've told us the point R divides PQ in the ratio 5 to 3. So what you're effectively saying is you're saying that this is 5 parts. From here to here is 5 parts. Oh, I'm on thick. 5 parts. And from here to here is 3 parts. Which means the whole thing is 8 parts. So you can start by writing something along the lines of P to Q is 8 parts. And then you want to find P to R. So you can write P to R is 5 parts. And then you can find the multiplier, and then you can form an equation, and then you can use the fact that you already know P to Q to find P to R, and then the rest of it should be straightforward. Okay, so I've helped you a bit with that question. Should be easy now. Okay, this is your question 3, and it's to do with equivalent vectors and parallel vectors. So it says OABC is a regular hexagon, so they're telling you this is a regular hexagon. And you can see that O to A is A, they've already labelled it on there, and O to B is B. M and N are the midpoints of OE, so this is the midpoint, and you can see they've done those, you know, those little dashes that you draw to say that that length there is equal to that length there, and again here that length there is equal to that length there. So they're telling you that M and N are midpoints. On your printout, label all the equivalent vectors. So where else are vectors that are equivalent to A? So I'll give you a bit of a clue. That's equivalent to A, and that's equivalent to A. So there are vectors there that are equivalent to A. What about vectors that are equivalent to B? Where are the vectors that are equivalent to B? Well, it should be obvious. Oh, I missed it. Never mind. I'm trying not to help you too much. Okay, so where are the vectors that are equivalent to B? And then just label them all. And it says there are 3 more vectors that are equivalent to A and 3 more equivalent to B. And you've got to find them all on your diagram and on your printout. You'll be able to find the printout from the link below. Show how you can use those equivalent vectors to plot a path from A to D. So we want to get from A to D, but what you'll find is we don't know this road. We know this road is A. We know that road is A. So this will be labelled on your diagram as also being A. So this will also be labelled as being A on your diagram. And this one will also be labelled as being A on your diagram. But you'll find we never actually know this route here. So it says how are you going to get from A to D? And you can still get from A to D by using some convoluted route. And in maths, it doesn't matter if you use a convoluted route. And then it says find the vector M to N and compare O to A and M to N. So have a go at that and see how you get on with that. Okay, vector addition and subtraction. In the quadrilateral shown, find the vector D to C. Okay, so what does this mean? Drawn by a moron? That's a bit cruel. Okay, usually these diagrams have diagram not drawn to scale, but I thought that's a bit boring, so I just wrote drawn by a moron. It's it rhymes. It's it's kind of a nice bit of nice way of representing it. So in other words, don't rely on the diagram, don't rely on the angles in the diagram, don't rely on the lengths in the diagram. Although the shape's drawn in the diagram like that, it might look completely different in real life. Okay, so it's just trying to say to you, look, the diagram is diagrammatic. You're not supposed to read anything from it, as in actual lengths or angles, or even if that shape is correct or not. You can tell that it's a quadrilateral the moment it just looks like an irregular quadrilateral, but it might turn out to be, might turn out to be something like a parallelogram. It won't, but it might turn out to be something like a parallelogram. Okay, so it says find the vector D to C. Now you can see that this route isn't labelled. We don't know that route. So although we'd love to go along, that's going off road. That's going off piste. You don't want to go off piste. It's dangerous. So we're going to go around this way instead. We're going to go around this way, around this way, around this way. Okay, so we are going to write D to C is, let's go from D to A first of all, and then let's go from A to B, and then let's go from B to C. Now this vector here is not D to A. It's A to D. It's pointing this way. So we need to change the sign of it. So negative a half P. So you see I've put a negative there. Don't miss that out. Plus A to B is this vector here, which is 3P minus 2Q. Plus B to C, that again, that's going in the correct direction, so that we don't need to worry about it. 2P minus Q. And then let's just tidy all of that up. D to C equals, what do you got? 3P plus 2Q is 5P minus half P is 4.5P, 9 over 2P. And what do we got for the Q's? We've got minus 2Q minus, so minus 3Q. Okay, let's factorize that. Remember, to factorize this, we need to do common denominator. So common denominator means I'm going to rewrite that as 6 over 2. Just rewrite that as 6 over 2. And rewrite that as 6 over 2. And then factorize out the 3 over 2, because 3 goes into the tops, and the over 2 is obviously the same in both of them. And so that gives me 3P minus 2Q is equal to D to C. And look at that. The first thing I notice is that brackets is the same as that brackets. So it says compare A to B, compare A to, it just keeps flicking back. I don't know why it does that. Compare A to B and D to C. So we know that A to B is 3P minus 2Q, and we know that D to C is 3 over 2 times 3P minus 2Q. So that tells us that D to C, so the multiplier here is times 3 over 2. So D to C, start with the A to B. A to B times 3 over 2 times 3 over 2 gives us D to C. So D to C is parallel to A to B, and D to C is 1.5 times the length of A to B. Hey, they're parallel. They don't even look parallel. And D to C is 1.5 times the length. No, that doesn't even look 1.5 times the length. Okay, so perhaps a more accurate diagram would be like this. A to B is here, and then D to C is here, like 1.5. Oh, that's probably a bit long. 1.5 times the length. And so our diagram probably looks more like that. In either case, if you've got two parallel sides, that leads you to a trapezium. So it says describe the shape ABCD. It's a trapezium. It's a trapezium. Okay, in the parallelogram, AB is equal to P plus Q. Yeah, it's drawn on the diagram. AC is equal to 2P minus Q. That's also drawn on the diagram. And they're telling us it's a parallelogram, and they're emphasizing that by, this is the sign of, that arrow is just a vector arrow, but this double arrow here tells you that they're parallel, and that single arrow there tells you the open arrow, the single open arrow there and the single open arrow there tells you that those two are parallel. It's a parallelogram. Find A to D. Okay, so again, I don't have a direct route for A to D. What I'm going to do, instead of trying to find A to D, is I'm going to say, look, you know, this vector here and this vector here are parallel. So what I'm going to do is I'm just going to slide that up to there and say, well, they're the same vector then. Yeah, that's the same vector. They're parallel, they're the same vector. And so now when I want to go from A to D, I'm going to go this route. I'm going to go this route here, and then this route here. Okay, so my vector from A to D is going to be A to D equals A to C plus C to D. And A to C I can see is 2p minus q. So that's going to be negative p minus q. So negative p, negative q. Okay, so that gives me A to D is 2p minus p, which is p, and minus q gives me minus 2q. So this is p minus 2q. So this vector from here to here is p minus 2q. P minus 2q. And that means this vector is the same. That means this vector is the same because they're parallel vectors. So that's going to be p minus 2q. Okay, it says find A to D, we've done that. Find D to B. Okay, so to go from D to B, I can go from D to A and A to B. So I'll do that. D to B equals D to A plus A to B. D to A is the negative of that, which is going to be negative p plus 2q. And A to B is plus p plus q. And then the negative p and the plus p cancel each other out, and that gives me 3q. 3q is D to B. Okay, and then it says find D to M in 3 different ways. Now obviously we don't need 3 different ways, but they're just saying, look, do it in 3 different ways just so that we can show that you get the same answer whatever way you do it. So the first and most obvious way I'm going to do it is I've just found D to B. So if I want to find D to M, instead of driving from D to B, I just drive halfway from D to B, and that will take me to M. So my first method is going to be D to M equals a half of D to B. So that's just a half of 3q, which is 3 over 2q. So there's my first method for D to M. Okay, my second method to get from D to M is I'm going to go this way here, and then half of A to C. Okay, so I'm going to go D to M, my second method. D to M is D to A plus a half of A to C. D to M, I already know, is the negative of that. So minus p plus 2q, minus p plus 2q, plus a half of A to C. A to C was 2p minus q. A to C was 2p minus q. And let's just tidy that up. That gives us minus p plus 2q, plus multiply that out gives me plus p minus a half q. And the minus p and the plus p cancel each other out. And so 2q minus half q gives me 3 over 2q. So you can see it's the same answer for D to M going that way around. Okay, so I went half of this route. Now I've gone this route. And now I'm going to go one more route just to say that we've done all 3 routes that they asked for. And the route I'm going to go this time is I'm going to go this way instead. So let's do it. I mean, the obvious thing is to go this way. That will be the obvious thing to go that way. But I'm going to just go really weirdo. And I'm going to go, let's go this way, and then this way. I mean, that's a bit of a nutty route, but still. Okay, so I'm going to go from D to M by going D to C, C to B, and then B to M. So D to M equals D to B plus B to C plus C to M. And D to B, I know is P plus Q. is P plus Q, plus B to C, that was P minus 2Q. But we're going the opposite way, so it's minus P plus 2Q. Minus P plus 2Q. Plus C to M is, well, it's the oh, hold on, I've written that right. D to C, C to B, B to M. D to C, D to C, C to B, B to M. Okay, B to M. Did we work out B to M? Well, we worked out B to D. Well, we worked out D to B. D to B was this here. So B to D would be the negative of that, and we want half of the negative of that. Plus C to M. C to M is minus a half of D to B. Minus half of D to B, which is plus minus a half times D to B. What was D to B again? It was 3Q. 3Q. Okay, let's just tidy that up. So that gives us P minus P, so they're going to cancel out. It gives Q plus 2Q is 3Q minus 1.5Q. So that gives us 3 over 2Q. So it's the same answer whatever way round we went. And isn't that what we said in the lyrics at the beginning? The long and winding vector route that leads us from A to B, it doesn't change its value no matter what path we see. The Beatles were thinking of vectors when they wrote that song. Oh, that's scary. Oh, gosh. Oh, hope you don't get nightmares from that. Okay, so it says OABC is a parallelogram and the length of A to P is twice the length of A to C. So, I mean, you can see that doesn't look right. That length does not look the same as that length there. I mean, if I draw it on the diagram, just draw that length there and then slide it up to there. No, they don't match, but that's what they do on purpose, is they say the diagram is not drawn to scale so that you can't read numbers of it. N lies on AB such that ONP is a straight line. Okay, so they're telling us that this has to be a straight line. Okay, so this has to be a straight line there. Okay, so N is actually probably, you know, more accurately here. Okay, so what we're going to do is we're going to find out the vector from O to N, and then we're going to find out the vector from O to P, and then we're going to say, look, they need to be parallel to each other. They need to be parallel to each other. They're actually collinear because they start from O. They need to be parallel to each other. That's how we're going to answer the question. So first of all, it's a parallelogram. So let's just do, you know, the obvious thing. That vector is B. That vector is A. And of course, we know that this vector, let's just, oh, hold on. Something went wrong there. That vector is B. Clone it. That vector is also B. I know it doesn't look like it, but just pretend it is. And that vector there is A. Okay, so, right, so let's first of all work out the vector from O to P. That will be easy to work out. So we'll work out the vector from O to P. O to P is O to A plus A to P, which is A plus 2B is O to P. Okay, now I'm going to work out this vector here. But before I can work out this vector here, I need to know what A to B is. So I'm just going to do that on the side over here. It's quite easy to do. A to B is A to O plus O to B. And so that's going to be negative A plus B, B minus A. And then what I'm going to do is I'm going to say A to N isn't all the way along there. It's just part of the way along there. So what I'm going to do is I'm going to say A to N is some fraction of A to B. I was thinking a half, but it's clearly not a half. And then I was thinking 3/4, and I thought, well, is that 3/4 or is it 4/5? And then I realised I don't actually know. So rather than put in all those numbers, why don't we just put in a letter, an algebra, a bit of an unknown, an x? Except we don't tend to use x as our unknown in vectors. We tend to use lambda or mu. Okay, so a to n is lambda times this, lambda times b minus a. Okay, and so now we can work out the vector from O to n. So O to n is O to A plus A to n, which is A plus, and then this was lambda b minus a. And then that gives us, that's not supposed to be there, so I'm just going to hide that. Okay, just hit that. And I'm just going to tidy that up. So that gives us O to n is a minus lambda a plus lambda b. I'm going to tidy it up a bit more. In particular, these are both, you know, like when you have 2x and 3x, they're like terms. So what I'm going to do is just rewrite that as being 1 minus lambda times a plus lambda times b equals O to n. Now I know these have got to be parallel. I know that O to p, which is a plus 2b, and O to n, which is 1 minus lambda lots of a plus lambda lots of b, I know that they have to be parallel to each other. So in other words, whatever number you multiply these by, the number in front of the a's, let's just put a little grey 1 in there because there's no number in front of the a, so I just put a little 1 in there. Okay, whatever you multiply those by is got to be the same as you multiply these by, the number in front of the b's. Yeah, the number in front of the a's has got to be multiplied by the same thing as the number in front of the a's, otherwise they wouldn't be parallel to each other. And so what I know is that the multiplier here is the second one over the first one. So 1 minus lambda over 1 is the multiplier here. And the multiplier here is again the second one over the first one, is lambda over 2. So these are my two multipliers, multiplied by. These are my two multipliers and multipliers, and these are my two multipliers, and they've got to be the same. If they're not the same, you're not going to get a parallel vector. So I'm going to make them equal to each other. And so that gives me, I'll just multiply through by 2. So that gives me 2 minus 2 lambda equals lambda. That gives me 2 equals 3 lambda, and lambda equals 2 over 3. Oh, so I was wrong. It was 2/3. So the answer is, it's 2/3. This is 2/3 of the way along here. So if you imagine that this is 2 parts, let's go to a pale colour and slightly fatter. If you imagine this is 2 parts, then this would be 1 part, and the whole thing would be 3 parts. And so this is 2/3. A to n is 2/3 of a to b. And so the ratio of a to n is 2 parts, and n to b is 1 part. So the ratio is 2 to 1. That's a really tricky question. If you understood that, and you get more in the class practice, then you've done brilliantly. Okay, so this is the class practice. This is your first class practice. And so it tells you that GH is 3HE, so that is 3 parts, and that's 1 part. And so the whole thing would be 4 parts. So you can use a little bit of the ratios thing there. This one, again, it's a ratios thing. Again, you've got to do, given MNC is a straight line, find P and Q. So this is like that other one where we had to find the lambda. And then this one is really tricky, really tricky. So when we do this in class, I'm really expecting the brightest students to help out a lot here. Okay, that's it for this lesson primer. Mena will see you at the weekend. I will see you with the next amazing introduction with like a song to the next lesson primer. Bye.